What is the magnitude and direction of the force between two parallel wires that are 45 meters long and 6 centimeters apart, each carrying 35 amps of current in the same direction? So this one's a little bit goofier because rather than finding the magnetic force on just one particle, now we're finding the magnetic force on an entire wire. And they didn't tell us what the magnetic field is, so we've got to figure that out ourselves too. There's two formulas on your sheet that I didn't really tell you why these are true in class. It's just a formula that I'm just going to give you that you just got to kind of accept. We didn't really have too much time to derive it. But let me show you those two formulas that you need. All right, so I got the two formulas listed here for you. And again, these are just grab them from your formula sheet. I wouldn't really wonder too much about why they're true, but hopefully they should make a little bit of sense to you. The magnetic field that's created from a wire, because anytime you have moving charges, you get a magnetic field. So if you have current going through a wire, the magnetic field that's created is mu naught divided by 2 pi. Mu naught is just a number that you can look up in your book. I'll throw that in a second. Times the current in the wire divided by how far away you are from it. So that makes sense. If you have more current or if you're closer to it, you'll get a stronger magnetic field from it. That shouldn't bother you too much. The force from a magnetic field on a wire, so if you have a wire that's carrying moving charges and it's in a magnetic field, then you get a force on it, and that's equal to the magnetic field, times how much current it's carrying, that should make sense too, times how long the wire is. So actually these formulas aren't all that complicated. Let me do a little bit more work and maybe I can put the whole story together for you. Okay, so a lot of stuff going on, but I looked up the value for mu naught in the back of a book, or you could Google it or something. It's 1.26 times 10 to the negative 6. And it's just a matter of throwing all these numbers in to find what the total force is. Be careful though, this thing was in centimeters, so make sure that you put in 0.06 instead of 6 or something like that. That would have messed you up. But the final answer on 45-meter long power lines, so that's half as long as a football field, is you only get a measly 0.2 newtons on them. That's really nothing. So these things weren't really carrying enough current to do the trick. It turns out current's the most important variable here, because check it out, it shows up twice. You got two eyes. But the force is very small. So the problem is asking us what the direction is on this force if they're carrying the current in the same direction. So you've got the two power lines going like this. You got the first one, we'll say they're both carrying it up. So they both have a current in the upward direction. And it wants to know what the forces are going to be. Well, they're either going to be attracting or repelling, because Newton said that forces come in pairs. So they're either both being pushed away or they're both being pushed together. Because you know the force has to be perpendicular to the current, perpendicular to the velocity that these charges are moving. But I got to teach you another rule to show you exactly how that's going to work. So let me show you that. Okay, so for the second right-hand rule, it's where you're trying to figure out what the direction of the magnetic field created from a wire is, where that magnetic field's going. It's actually going all over the place. It's going in a loop around the wire. But the way that you do it is, in this case, your thumb is actually going to represent the direction of the current. So your thumb is now where the current's going in the wire. And there's actually only one other thing. The other thing is going to be, I like using my middle finger. Some people use their whole hand, but whatever works for you. This is going to represent the direction of the magnetic field created by that wire. And it turns out that you get a magnetic field created in all sorts of different directions. So, for example, if you have a wire that's carrying current this way, then if you're on this side of the wire, the magnetic field's that way. If you're on top of the wire, it's this way. If you're underneath the wire, it's that way. The magnetic field goes in a circle around the wire. Let me see if I can draw that a little better for you on the board. So on the example of this particular wire, if the current is going up, then you throw your thumb in that direction of this arrow. And if you put your hand this way, then the magnetic field is going into the board. So what you see is the X's on the arrows that you're shooting. And then if you put it this way, your middle finger is going out of the board. So that means the arrows are being shot at you, so you see the point of it. So you can pause the video and see a description for what force you get on the second wire. And by Newton's third law, you get the same force on the first wire the other way.